Hi, hello, good afternoon, one and all. Welcome to the session. Can you confirm about this audio and video if everything is clear? Is this clear? If everything goes well, then we will start the session. Hi, please do let me know if anybody is there so that we can move on. Good afternoon, Dian. How are you? All right. Chalo. So if everything goes well, then we'll move on. So in the last session, we had a discussion on parallel DC circuits. Or DC networks. So there we try to calculate the total impedance, or other in the form of impedance and in the form of admittance we calculated, and then later we have calculated the current through each and every branch, and then we have calculated the voltage, and then later of course even we have calculated about the power dissipation also, and we have got some conclusions like the least resistance path is going to capture large amount of the supply current, and the highest resistance path is going to capture small amount of the power and small amount of the current also. Okay, and the voltage across each and every branch in the parallel connection will be same. Okay, and it is not just because of voltage is same, and it is not just because of current division. We are not going to call it as a parallel connection. It is something other that it is something other than that. That is, if any two elements are there, the two elements terminals should have a two common points. Then only you can call it as a parallel connection, because voltage can be same in the adjacent part also. Current can be divided in the other adjacent part also. So current division is okay. Current division is fine. Current division is fine. So in that way you can say. All right. So these are the some points we had a discussion in the parallel DC circuits. The same points even quite applicable here also, but the only thing is you need to look into inductive reactance and the capacitive reactance. Okay. So let us take up them. Let us take up them. So we will take up small, very simple questions, and then from tomorrow and day after tomorrow, we are going to take up very good questions on series and parallel combination of AC circuit as well as DC circuits. Okay, and before moving on to the session, there's a small introduction about myself. My name is Naveen Gollapally. I have 7+ years of experience in teaching. Most of the times I'll be teaching networks, measurements, machines, and power systems. All right. So look into this one so that we can move on. Hi, hello everyone. Please let me know your presence so that we can move on, my dear. Okay. So anybody is there, please now try to tell me the answer. What is asking? What is asking? Is asking. Calculate the input impedance, draw the impedance diagram, and find the admittance of each parallel branch, and determine the input impedance and input admittance and draw the admittance diagram. So in the last session I said when the elements are connected in parallel, their conductances addition can be easy. Addition will be easy. So similarly here also I have a resistor. So this resistor has a one common point. Resistor and inductor has a one common point. Here also one more common point. Their terminals are connected twice. So two common points are there. Therefore they are said to be in parallel connection. Now you can add their admittances, or you can add their conductances easily. Okay, so what is the conductance of this one? 1 by R, it will be 20 ohms. What is the conductance of this one? You have to do not forget J. So do not forget J. So 1 by J10, it will be minus J 0.1 mhos. So this is, I'm so sorry, this is 1 by R, 1 by 20, and this will be 0.05 mhos. So I have got individual there. We call it as reciprocal of resistance, as we call it as conductance, And reciprocal of inductive reactance, we call it as inductive susceptance. We represent with B. We represent with B. So the total admittance is going to be G, and this is minus J, na? So minus JB, G minus JBL. So it is of 0.05 minus J 0.1 Siemens. Okay. It is asking even impedance also. You after getting admittance, you reciprocate it. Just get the reciprocal of this one. Reciprocal of this one. So 1 by YT, our total admittance, is equals to total impedance. Now, can you take up this 0.05 minus J 0.01? Reciprocal of this one. How do you do this one? Reciprocal of this one. You know, for a two elements, you can do it simply like R1 into R2 divided by R1 plus R2. That is also fine. When you have multiple elements like 3 elements, 4 elements and 5 elements, there is a best option. Add their admittances, then go for reciprocal. Go for reciprocal. Okay. How do you do this? So far, is it clear? Is it clear for everybody? Hi, Arun. Now coming to this point, if you wanted to take up impedance, I'm going to do like this. So I'm rationalizing here. That is with the 0.05 plus J 0.0. It is 0.1 itself. I'm so sorry. It is 0.1 itself. So 0.05 plus J 0.1. I'm multiplying and dividing with the same value but opposite sign. All right. Then if you do so, it will be the denominator is looking like A minus B into A plus B, like A minus JB into A plus B. So what will be the denominator? The denominator will be, you are going to get it as A square minus B square, but we have got plus J and minus J. So it will be B square plus B square, na? A square plus B square. So you are going to get 0.05 whole square plus 0.1 whole square. Now in the numerator we have got it as 0.05 plus J 0.1. So you can separate this one now. ZT is equals to 0.05 divided by this total magnitude, of course 0.05 square plus 0.1 square plus J 0.1 divided by 0.05 square plus 0.1 square. So this is the total impedance. There is a total impedance you are going to get. Is it clear so far for everyone? Respond, my dear. Is it clear? So this is how you are going to calculate impedance. Or otherwise simply R1 into R2 divided by R1 plus R2 you will do, na. In the same way you can also do. I'm taking it for multiple elements. For whenever you have multiple elements, this is a better option. Like, okay. Right. So let's see. And what is asking? Find the admittance of each parallel branch. We have seen find the admittance of each parallel branch. What is the input impedance? We have calculated input impedance also. Now is asking, sorry, input admittance and draw the admittance diagram. So this is the input admittance, total input admittance. The diagram will be like this. So let me draw the diagram. Real term is there, imaginary term is there. So real term and imaginary term. 0, 90 and so on, right? So I can take up the conductance on this one. This is G, that is 0.05. Next, inductive reactance, that is inductive susceptance, that is on the negative side, minus J. So it is around 0.1. This is BL. Now resultant of these two is the total admittance. You can take up even similarly for impedance also. You take up the real term, imaginary term and take up the resultant. Okay. So this is how you can do simply. Now can you do the same thing for this one? Can you calculate the total input, total admittance and impedance, and then draw the triangles. Try to draw the triangles. Try to draw the triangles. I am taking now 1 by g, it will be 1 by 5. So you are going to get it as 0.2 mos. Here 1 by jxl, so you are going to get it as minus j 1 by 8 mos. Similarly here minus jxc, na, this is minus jxc, so 1 by minus jxc, you are going to get it as plus j by 20 mos. So these are the conductance of the resistance or admittance of each and every branch. Now you can add up them. You can add up them. So the total admittance is going to be 0.2 mos minus j 1 by 8 mos plus j 1 by 20 mos. So this is the resultant admittance. You can add up the j parameter. You can add up the j parameter. How much you are going to get? Can you tell me how much you are going to get? So let me take up that one. So 1 by 8, 1 by 20. 1 by 20 is going to be 0.05. 0.05 minus 1 by 8. I'm going to get 0.075. So 0.2 minus j 0.075 mos. This is the total admittance. If you want to draw the admittance triangle, you can draw the admittance triangle also. You take up the reference. Take up the reference I'm taking here. The real term, imaginary term, positive imaginary term, negative imaginary term. Okay, I'm hiding. Now, G will be here. This is G. So let me take up G as 0.2. Next, I have got inductive susceptance. The inductive susceptance is 1 by 8. 1 by 8, it seems like how much it is? How 1 by 8 is around 0.125. So 0.125. So minus j 0.125. Maybe 0.125, obviously less than the G. So let me take up G some more longer. This is inductive susceptance. Okay. Now 1 by 20 is 0.05. So 0.05 is going to be this much. Let me take up, this is going to be the capacitive susceptance. Now the capacitive susceptance and inductive susceptance both are equal, also both are opposite, not equal, both are opposite. So some part is going to be compensated. Now the remaining part is going to be, maybe I can take up this as BL minus BC. BL minus BC. Now if you take up the parallelogram law, so this is going to be the resultant admittance. So this value you are going to get 0.2 minus j 0.05 you are going to get. Got it, my dear? 0.2 minus j 0.05 mos you are going to get. Similarly, after calculating YT, then you can calculate impedance also. You can calculate impedance also. Alright. Or otherwise, instead of doing this one, there is another way also. I can take up that. There is another way also. Generally, when you have elements, more than 2 elements, for only 2 elements, we will do it as R1 into R2 divided by R1 plus R2. In the same way, if you want to do, like if you do not want this one, in the same way, if you want to do, let me show you. I am just taking resistors. You can do it for even inductors, capacitors also. Like when you have like this. First, I'll take up for resistor R1, R2. So how do we write this one? 1 by R1 plus 1 by R2. So R1, R2 divided by R1 plus R2. So if you reciprocate it, you are going to get it as the R equivalent will be R1, R2 divided by R1 plus R2. Now for this, I am going to add an extra element. I am going to add one more element, that is R3. Already I have a parallel combination of R1 and R2. Now I am going to join R3. So that is for with respect to this quantity that is in parallel with now this one. So R3 is in parallel with this one. So into R3 divided by R1 R2 divided by R1 plus R2 plus R3. This is how you have to do. So if you want to minimize this one, you can minimize still. If you do this one, if you minimize this one, R1, R2, R3. So in the numerator you are going to get R1, R2, R3. Denominator what is there? R1 plus R2. R1 plus R2. Now in the numerator, actual numerator term, this term I am simplifying. R1, R2, if you multiply with R3, you are going to get it as already this one R1, R2 plus R3 into R1 plus R2 into R1, sorry, R2 into R3 divided by R1, R2. This one, this part, R1, R2. That is R1 plus R2, I am sorry, R1 plus R2. So, you can cancel out this one and you are going to get simply, if you have n number of elements, what you have to do is like this. If you have three elements, then the three elements product divided by sum of these two, sorry, product of these two, next product of these two, next product of these two. R1, R2 plus R2, R3 plus R1, R3. So like that you can do. Similarly for this one also you can take up. The same impedance, same admittance you are going to get. Same impedance, same admittance you are going to get. So let me show you that. I am erasing this one. This is the formula. R1, R2, R3 divided by R1, R2 plus R2, R3 plus R1, R3. If you have inductors, capacitors, you just include the J term, that's it. You need to take up the oppositions. Okay, so let me take up here. Now the total Z is equals to R1, R2, R3. So it will be 5 into plus J8, do not forget J8, plus J8 into minus JXE, that is minus J20. Product of these three divided by R1 into R2, that is 5 into J8 plus R1 into R3, 5 into minus J20 plus R2 into R3, so that is 8 into minus J20. So this is the total impedance you are going to get. Is it clear so far, everybody? Come on, my dear, respond. Respond, my dear, respond. So that we can move on to the next one. All right. So that is how you can calculate the impedances in the parallel connection. Let's see the current division rule. I'll show you the current division rule for two elements. I'll show you the current division rule for three elements also. Two elements you can do it easily. Okay. Two elements you can do it easily. For three elements also, if you know it, then that will be easy. So let us take up first two elements, then we'll move on to three elements. R1, R2. So if I take up some small DC source, you can take up AC source also, no issues. In the last session we concluded that voltage across R1, voltage across R2 will be same. Okay, so if you take up this as V1 and V2, V equal to V1 equal to V2, because they are connected in parallel. If you apply KVL, it will be same. Now we need to calculate current flowing through R1, current flowing through R2. If the source is going to deliver current I, What is the current flowing through R1? What is the current flowing through R2? So let me take up this one. Let me take up this one. If you wanted to calculate I1, voltage across that resistance divided by that resistance simply. So it is I can write it as Ohm's law, V1 divided by R1. What is V1? I can write V1 as V, the supply voltage, divided by R1. What is V? You can write the V in terms of current into total equivalent resistance. Current into total equivalent resistance. So I can write here I into total equivalent resistance divided by R1. What is equivalent resistance? Just now we have seen equivalent resistance of two resistors will be R1 into R2 divided by R1 plus R2. So let me represent that one. R1 into R2 divided by R1 plus R2 divided by R1. So R1 is going to be cancelled. Now you can have I1 is equals to source current into R2 divided by R1 plus R2. In the same way, if you do for I2, similarly for I2, you are going to get I2 is equals to source current into R1 divided by R1 plus R2. In other words, we say simply when you have only two elements, if you wanted to calculate this R1 current, the total entering current, how much current it is entering at this junction, that entering current into opposite resistance divided by total resistance. If you wanted to calculate the current flowing through R2, total entering current at the junction into opposite resistance divided by total resistance. So that is what we have taken. See here, total entering current into other resistance. I wanted to calculate current through R1. So entering current into other resistance divided by total resistance. Similarly here also. Okay, got this point. So similarly you can do it for three resistors also. Similarly you can do it for three resistors also. Similarly you can do it for three resistors also. Let's check for the three resistors. Are you ready? Guys, tell me. R1, R2, R3. We know equivalent resistance of these three resistance. How? R1, R2, R3 divided by R1, R2 plus R2, R3 plus R1, R3. So that is the total equivalent resistance. So let us take up for three resistors also. Now now I1, this will be I1, this will be I2, this will be I3. Okay, chalo. If you wanted to calculate current flowing through R3, of course, here voltage across each and every resistance will be same because they are connected in parallel. Yes or no? Okay. Now moving on, I am calculating. You can calculate each and every current also. I am calculating I3. I3 is equal to V3 divided by R3. What is V3? Source voltage divided by R3. What is the source voltage? How do you write? Source voltage is equals to source current into total equivalent resistance. So again I can write here I into R equivalent divided by R3. What is the R equivalent of the three resistors? What is the R equivalent of the three resistors? We have seen already. That is I3 is equals to I into R equivalent is R1, R2, R3 divided by R1, R2 plus R2, R3 plus R3, R1 or otherwise R1, R3. Yes or no? This is the formula or not? Divided by what is the left out? R3. So you can now cancel out this one R3. Then you are going to get I3 is equals to total current into R1, R2 divided by R1, R2 plus R2, R3 plus R1 into R3. So which is missing here? If they are asking if they are asking current to through the third element, that is R3 is missed in the numerator. Then rest is going to be same. S is going to be same. So entering current into R1 R2. So opposite resistance, opposite branch resistance product divided by total. So that is R1 R2 plus R2 R3 plus R1 R3. Similarly, if they are asking the current through R2, that is I2, then entering current into how you are going to get entering current into, can you tell me entering current into what is the resistance to be taken? R1 and R3 you have to take, R1 and R3 divided by R1 R2 plus R2 R3 plus R1 R3. This is going to be same, numerator. Yes or no? Is it clear, my dear, so far? Is it clear, everybody? Respond, my dear, respond. I think it is so slow, it seems like so slow. Let me check in the even mobile so that I am getting yes. Respond, my dear. Clear? Chalo. But here also, even mobile also, I am getting so slow response. Okay. So this one, similarly, you can calculate for I1 also. So total entering current into other branch resistance, R2 into R3 divided by R1 plus R2. Sorry, R1 R2 plus R2 R3 plus R1 R3. In the same way, even you have inductive reactance, capacitive reactance also, doesn't matter. You just take up the J notations, including J notations, you have to take up. Okay, chalo, do this one now. Do this one now. Using current division rule, find the current through each impedance. Find the current through each impedance. I want current through resistance. So IR is equals to entering current into opposite branch impedance. What is that opposite branch impedance? JXL. Remember this one, JXL divided by R plus JXL. So you are going to get entering current is how much? 20 amperes at an angle 0. A2. JXL is how much? 4. So J4 divided by R plus J4, that is 3 plus J4. This is the current. There is a current. Of course, you have to solve it and you have to get the value. So this is 4 into 220, it will be 80. 80 at an angle 90. Numerator 80 at an angle 90. Denominator will be 3 square plus 4 square. 9 plus 16, 25. Root of 25 will be 5. And 5 at an angle 4 by, that is tan inverse of 4 by 3. It will be around 53.13, yeah. Tan inverse of 4 by 3. Yeah, 53.13. Now the current is going to be, I think 16 phi's. So 16 at an angle 90 minus 53.13. I'm getting around 36.86. So the current flowing through the resistor will be 16 at an angle 36.86. Can you tell me what is the current flow through the inductive reactance now? Can you tell me? Come on, my dear. Can you tell me what is the current flowing through inductive reactance now? How do you take up now? Current through the inductive reactance will be total entering current, that is 20 at an angle 0, of course, into the other branch resistance 3 divided by 3 plus J4. Already we did 3 plus J4, that is 5 at an angle 53.13. So if you do this, 20 into 30, sorry, 20 into 3, it will be 60. So 60 by 5, you are going to get 12. 12 at an angle minus 53.13. So this is how the inductive current and this is how the resistive current are going to exist. Okay, with respect to what this is, resistive current is going to lead with respect to source current by 36.86 degrees. Inductive current, that is the current flowing through inductive nature, is going to lag with respect to source current by 53.13. If you take up source current as reference, let me show you that. if you take up source current as reference, from this current, from the source current, the resistive current is going to lead by 36.86. So here is the resistive current nature, and this is 36.86. Now inductive current is going to be minus 53.13. So minus 53.13. This is IL. Minus 53.13 means you have to take up in the clockwise direction, lagging side, right? Now you add the angle between resistive current and inductive current. You are going to get 90 degrees. So the angle between resistive nature current and inductive nature current will be absolutely 90 degrees. No doubt at all. So you have to get like that. Okay. So you can cross check like that also. Now can you tell me what is the current through this branch? Can you tell me what is the current flowing through this branch? Using the current divider rule, find the current through each impedance. Find the current through each impedance. So this branch current, you just make it as I1. This branch current, you just make it as I2. So how much current is entering here? How much current is entering here? 5 at an angle 30. So can you tell me what is I1, or can you tell me what is I2? I1 is going to be 5 at an angle 30, 5 at an angle 30 into 5 at an angle 30 into opposite branch. What is this opposite branch reactance? Minus J2. So be careful. Do not forget minus J divided by total impedance. That is minus J2 plus 1 plus J8. So you are going to get 5 into 2, 10. 10 at an angle minus 90 plus 30. This is minus J is nothing but you can write it as 2 at an angle minus 90. Now, yes or no? So 5 2s are 10. Minus 90 plus 30. So you are going to get minus 60 degrees divided by this will be 1 minus J6. 1 minus J6. So you can take up the magnitude also. So 10 you are going to get, okay, of course, sorry, 6 square plus 1 square, it will be 37, root 37, 6.08, 10 divided by 6.08. I'm getting around 1.61, sorry, 1.643. At an angle of minus 60 in the numerator, and denominator angle how much? Tan inverse minus 6. Tan inverse minus 6, I am getting it as minus 80.53. If this minus 80.53 goes up, it will be plus 80.53. So plus 80.53 minus 60. So you are going to get it as 20.53. So this is how the current looks like. 20.53. Similarly, can you tell me what is I2? Can you tell me what is I2? Yeah, okay. Plus J6. Yeah, plus J6. Oh, 20.53 means minus 80.53 minus 60. You are going to get very, both are going to be minus. So minus 60 minus 80.53. How much you are going to get? 140.53. So this is the current. Now similarly you can calculate for the other one. Current flowing through capacitive reactance. Can you tell me what is the current flowing through capacitive reactance? I2 is equals to entering current, that is 5 at an angle 30, 5 at an angle 30 into opposite impedance, this branch impedance, that is 1 plus J8 divided by, here we have already did this one, minus J2 plus 1 plus J8, you are going to get it as 1 plus J6. So 8 square plus 1 square, that will be 64 plus 1, 65, root 65, 8.06, 8.06 into 5. I am getting around magnitude as 40.31, numerator magnitude. Now phase angle tan inverse of 8 tan inverse of 8 just now we tan inverse of 8 is 82.7 82.7 plus 30 degrees. Angles can be added, no, these angles can be added. So we are getting around 112.87 divided by, we did already this 6 square plus 1 square will be root 7, sorry, root 37. We are getting around 6.08 at an angle minus 80.53, yeah, something, yeah, plus 80.53 plus 80.53. So 40.31 divided by 6.08 will be 6.62, and the angle you are going to get it as 112.87 minus 80.53, 32.34. So these are the currents you are going to get. Okay. Okay, my dear, is that clear so far? You can very rare, but you can expect this kind of questions for 1 mark. It's current division, because in the examination you do not have. They are not going to avoid the scientific calculator. So definitely virtual calculator. It will be very tough. So please habituate with have virtual calculator. That is gate virtual calculator. Okay. So where you do not have this rectangular form, polar form conversions. The only thing is you have to do magnitude and phase angle. Definitely you have to do tan inverse, use tan inverse. For the magnitude you have to use square root of x square plus y square. That is the only option. So please take care of this calculations. Okay, please be habituate towards virtual calculator. Then I think you will not feel difficulty when you are attempting the examination. All right. Okay, my dear. Right. Moving on. For the network shown in the figure, determine y of t and z of t. Sketch the admittance diagram. Find E and IL. Compute the power factor of the network and power delivered to the network also is asking. Let us see the network. This is how the network is. So he's asking total impedance admittance. Yeah, impedance admittance diagram also is asking. So let us calculate impedance. Let us calculate admittance. If you wanted to calculate impedance or admittance, no issues. If elements are connected in parallel, for 2 elements it is not a big deal. For 2 elements it is not a big deal. For 3 elements also it is not a big deal. We have 6 elements. You can replace the 6 elements with 3 elements because this 10 and 40 are in parallel. Of course, all are in parallel. I'm replacing the 2 resistors with single resistor. So it will be 10 into 40 divided by 10 plus 40. 400 divided by 50. So 400 divided by 50, you are going to get just 8 ohms. Okay. Now similarly here also, inductors, 2 inductors, you can replace with single inductor. 6 milli, you can take up 6 milli, L1, L2 divided by L1 plus L2. So that is 6 milli into 12 milli divided by 6 plus 12 milli. 72 divided by 18. I think you can do it. How much value? 9 2s, 9 8s, 9 8. Will it go 9 8? Yeah. 2 4. 9 2s. Yeah, 9 8s. 2 4s. 4 millihenries. Now capacitors are connected in parallel. So quite opposite to resistance. When the resistors are connected in parallel, you have to die like this. When capacitors are connected in series, you have to write C1 into C2 divided by C1 plus C2. But here it will be C1 plus C2. So how much it is? 8 micro plus 20 micro. Sorry, 80 micro plus 20 micro. You are going to get 100 microfarads. So two resistors can be replaced with one resistor. 2 inductors can be replaced with one inductor. 2 capacitors can be replaced with one capacitor. Now only 3 elements I have got. Right. So I'm replacing here 8 ohms, 4 millihenries, and 100 microfarads. Just now we have seen for three elements how you are going to connect, how can you calculate the impedance. You can calculate impedance, you can calculate admittance also. Okay, first convert them into ohmic values. What is the ohmic value of this 4 millihenry? This will be j omega l, that is j xl is equal to j omega l. J omega is how much? 1000 radians per second. The current delivered by this current source is of sinusoidal function and it is of having a frequency of 1000 radians per second, angular frequency. So j 1000 into 4 milli. Milli 1000 gets cancelled, you are going to get j 4 ohms. Similarly, jxc minus jxc, you are going to get it as 1 by j omega c also you can write, or minus j by omega c. Omega is 1000, c is 100 micro. So this is 10 to the power of 5 and 10 to the power of minus 1 remains. If 10 to the power of minus 1, that is 0.1. If it goes up, this will be 10. So minus j10 ohms you are going to get. You can replace this with minus j10. You can place it as j4 ohms. We have oppositions. You just convert them into admittances. So its admittance is going to be, this admittance is going to be 1 by 8. This admittance is going to be 1 by j4 and this admittance is going to be 1 by minus j10. If you add up, let me hide and let me add up. So the admittance, total admittance is going to be 1 by 8 mos plus 1 by j4 mos plus 1 by minus j10 or minus j10, yeah, minus j10 minus j10 mos. Can you tell me 1 by 8 how much this will be? 1 by 8, 0.125, 1 by 0.125. This will be minus j 0.25 because 1 by 4 is 0.25 na? And this will be, if this j goes up, plus j 0.1. So inductive susceptance is greater than the capacitive susceptance. If you want to draw the impedance triangle, admittance triangle, you can draw the admittance triangle also even. If you want to draw the admittance triangle, you can draw the admittance triangle also. So G is this much, inductive susceptance is this much and capacitive susceptance is this much. So G is 0.125, which looks like 0.125 is a smaller of course. So this is G. Minus JBL, so 0.25. Compared to capacitive susceptance, inductive susceptance is dominating. So I am drawing it bigger. Okay, so this is BC. Now BC and BL are opposite. So some part of the BL is going to be compensated. Now the equivalent is going to be BL minus BC. Now you are going to get, this is the resultant or total admittance. You can take up this one, 1 by 0.125 minus j 0.25 plus 0.1 minus j 0.15. Okay, so this is the admittance. You can still simplify this one. I said na, you can still simplify this one. You can take up the same value with opposite sign, that is 0.125 plus j 0.15 divided by 0.125 plus j 0.15. You can divide that one. Okay, so you'll get R separate, that is conductance separate and the susceptance separate. Okay, so this is how you can calculate total admittance. Let us calculate impedance. We have three elements. Calculation of impedance is so easy. Let us do that one. Total impedance is going to be R1, R2, R3 divided by R1, R2 plus R2, R3 plus R1, R3. So what is R1? 8 ohms. What is R2? This is like a R1. This is like R2. This is like R3. You just do it. No need to write inductive reactance and capacitive reactance. But simple, remember that it has a J notation. So 8 into J4 into minus J10 divided by 8 into J4 plus 8 into minus J10, R1 R2 plus R1 R3 plus R2 R3, that is J4 into minus J10. This is what you are going to get. So you can simplify still. So this will be 10 into 4 will be 40, 40 into 8 will be 320. Minus j into minus j, j into j square minus 1. Already minus is there, so plus. So 320 divided by, you can take up this one, 32j, j32 minus j80. And this one, j into j square is minus 1, and minus 1 into minus will be positive. So you'll be getting it as 40 plus 40. So you are going to get the total impedance as 320 divided by 40 minus 80 minus 30. It will be 50, and of course 48 minus j48. Minus j48. Still you can reduce this one. Because I wanted to get in terms of like, our resistance and inductive nature, Still, if you wanted to reduce, what you have to do? Go for rationalization. Go for rationalization. Okay. Are you following me, my dear? Hi, Ashok. So go for rationalization. 40 plus j 48 divided by 40 plus j48. Now, of course, you are going to get here it as this denominator, you are going to get this as 40 square plus 48 square. Now, here real term is there, imaginary term is there. So, real term is 320 into 40. 320 into 40 plus j, imaginary term, that is 48 divided by this term, anyhow denominator repeats again, that is 40 square plus 48 square. So this is going to be the total resistance term, and this is going to be the total inductive reactance term. Sometimes I'll ask you like this also, what is the equivalent resistance of the network? What is the equivalent inductance of the network? Okay, they'll be giving you like this. What will be the series equivalent resistance? What will be the series inductive network? This is a series equivalent resistance. So you will replace this as like a resistance and inductance, entire values. So this is RT and this is total XL, or I can write XC, XT. So 6 elements can be replaced with this single element. RT is this much, XT is this much. How can you say that it is inductor? Because I am getting positive J plus J. If I get negative J, I would have called it as capacitive reactance. Is it clear for everyone, my dear? Hi Santosh, how are you? Is it clear for everyone? All right, moving on. Yes. Same way you can do this one. Draw the phasor diagrams of the IS, IR and IL. You can, we just did now current division. If you want to do, you can do current division also, and then take up the phasors. Generally, the network is looking like parallel network. So in parallel, voltages are common. Voltage across the resistance, source voltage, and voltage across inductance, all are same. Source voltage, let me write it as E. Voltage across resistance and voltage across inductance, all are same. Now current through resistor will be in phase with the resistor, in phase with the resistance voltage. Current through inductance will be lagging with respect to voltage across the inductor. So like that you can take up. Okay. Chalo. So we have a total current also. We have a total current also. Now you can calculate the current division. Total current and current division, if you want to calculate, you can calculate. IR is equals to 2 at an angle 0 into J20 divided by 10 plus J20. So you'll get some angle. So this resistive current is going to have a displacement with respect to source current. With respect to source current. Okay, be careful. Next, inductive current 2 at an angle 0 into opposite arm, that is 10 divided by 10 plus J20. So whatever the angle you are going to get, you are going to have here or here. So inductive current is going to have some displacement with respect to source current, because I am taking source current here. Okay. All right. In a general manner, how do you draw? In a general manner, how do you draw? Let me show you. As voltage across each and every branch is same, I am taking voltage as reference, that is source voltage, resistance voltage and inductance voltage as same. Now the current flowing through the resistance will be here. This is going to be IR. You will get some IR magnitude you can take up. But be careful, whatever the angle you are going to get, that angle is displaced with respect to source current. Be careful that one. Okay, I'll show you that source current also. Now IL, where should be IL? IL will be like here. It should be lagging with respect to inductor voltage by 90 degrees. This is how IL. How much lagging? It should be 90 degrees. Now the resultant current is going to be IR plus IS is equal to what? IR plus IL only. We have calculated IR, we have calculated IL also. So the resultant current is going to be IS. This is the IS. So from IS, if you move in anti-clockwise direction, the resistor current is leading by some angle. If you solve, you'll get to know. You'll come to know. Okay. So 2 into 20, it will be 40. 40 at an angle 90. Numerator is 40 at an angle 90. Divided by denominator 10 square plus 20 square. 500, of course, root of 500 will be 22.36. What is the angle? 20 divided by 10, that means about tan inverse 2. Tan inverse 2 will be how much? 63.43. So 40 divided by 22.36. I am getting a magnitude of 1.78 at an angle of 90 minus 63.43. So I am going to get it around 26.57. So IR current, the current which is flowing through resistance, is going to have a displacement of 26.57 with respect to source current. So this angle is 26.57. All right. Similarly, you can calculate inductive current also. Okay, you can this is the inductive current. This is the inductive current. You can draw parallelly like this inductive current. This is the inductive current. Now you see, from the inductive current, the source current is leading. Or otherwise, inductor current lags with respect to source current. You have to get negative angle here. So 2 into 10 will be 20. Okay, 20 divided by this magnitude. What is the magnitude I have got? 22.36 at an angle how much? 63.43. So if it goes up, minus 63.43. So this will be obviously minus 63.43. So current, inductor current is lagging with respect to source current by minus 63.43. There's the same angle here also. This is the inductor current and this is the source current. Okay, source current is going to lead with respect to inductor current, or inductor current is lagging with respect to source current. Everything is okay, fine. Okay, so these are your phasors IS, IR and IL. What is E is here. So verify Kirchhoff's current law at node. At this junction, verify. How to verify? 2 at an angle 0 is equals to IR and IL. IR how much I have got? 1.78 at an angle 26.57 plus, what is this? 20 divided by 22.36. 20 divided by 22.36. I am getting 0.89 at an angle minus 63.43. As we do not have a scientific calculator, how to check this one? There is no option. You have to convert this into r cos theta format. R at an angle theta into r cos theta plus j r sin theta. Similarly here also r cos theta plus j r sin theta, that is 1.78 into cos 26.57 plus 1.7 into sin 26.57. So if you calculate, then you will get real term, imaginary term, real term, imaginary term. End of the day, you will get real term, imaginary term. Then solve it, you will get the, again convert into polar form. So you will get this one. Magnitude wise, you see 1.78 and 0.89. It will be very near to 2. So here it is 26.57 and 63 minus 63.43. So just now we have seen the resultant, right? Here is the resultant. You see, so IR current and IL current, the resultant is the source current. So be careful, this angle is not with respect to source voltage, this angle is with respect to source current minus 63.43. this angle also with respect to source current 26.57. Okay, is it clear for everyone, my dear? Yeah, here I missed 320. Thank you. Thank you, Kamal. 320. Is it clear for everyone? All right. Let's move on. So that is how you can. I know it is without scientific calculator it is not easy, but you know why I am giving this questions, because if you are from electrical engineering, you'll realize, you know, this calculation you'll realize in the power systems, especially the transmission line calculations, or yeah, during transmission line calculations only, especially, and that too voltage control parameters. When you have a network as RL nature, if you are adding capacitor, how it is going to be, not only just voltage and current variations, but they'll ask you the power variations also. Okay, by adding capacitor, how the voltage is going to be changed, how the active power and reactive power flow is going to be changed, or which power is going to be influenced. That kind of questions you can understand easily. Okay, if you analyze this RC circuits, RL circuits, you'll come to know what is when it is RL circuit, how is the power flow. When it is RC circuit, how is the power flow. You'll come to know. Okay, so once you get the voltage across this, voltage across resistance and voltage across capacitance. Okay, current into resistance, now you have a current, source current, so use current division rule. You can find out current through resistance, you can find out current through capacitance. That source current, that current, resistance current into resistance, you are going to get voltage. So that voltage is nothing but source voltage. That voltage is nothing but source voltage. So once you are going to get source voltage, E, VR, VC. So the power you can calculate. Apparent power is equal to source voltage into source current. If you multiply with cos theta, you are going to get active power E into Is into cos phi. Angle between source voltage and source current only. Reactive power is going to be E into I into sin phi. I'll show you this power calculations when it comes to series parallel, both the combination. Okay. Here it will be so easy, because once you know, we already did this one here. We already did this here. We know source voltage. How much is the source voltage? This current into resistance, you just multiply. So 1.78 into resistance, that you are going to get 17.8 at an angle 26.57. So 17.8 is the magnitude, source voltage magnitude, right? Okay, so source voltage magnitude is 17.8 volts. Source voltage magnitude. Now you know the magnitude, you know the source current. Where is the source current? This is the source current, right? So source voltage into source current is angle between source voltage and source current. How much? This is the angle between source voltage and source current. Okay, 26.57. So 17.8 into total source current is 2 amperes into cos of 26.57. So that is active power. V into I, that is apparent power. V into I into sin phi, that is a reactive power. So likewise you can do. Okay, so try this one. At least try for resistance current, capacitance current, and then calculate E. Be careful. Whenever you wanted to calculate Jxc, 1 by j omega c, we have got omega also, j2 pi f c. So substitute this f, 60 hertz is asking. C value is 0.13 microfarad. So be careful. Okay, my dear. So this is finding out some currents and impedances. Similarly, the next question also is asking draw the phasor diagrams of IS, IR, IL, IC. If you have three elements, so far I have got only RL or otherwise RC. If you have three elements, how it will be if you have three elements? Let me show you. We have a omega, that is 377 omega, right? So we have capacitive reactance, we have inductive reactance also. According to that, you can calculate currents also, right? Let me show you the impedance or admittance triangle. You can take up admittance as 1 by J2, it will be minus J.5 mhos. This is 1 by minus J5, so it will be J.2 mhos. 0.2 mhos is lesser than this one, obviously. Obviously, inductive reactance is smaller value, capacitive reactance is larger value. So obviously, its admittance is smaller. Reciprocal, admittance is smaller. So if you take up admittance phasor, G is 1 by 1.2, right? So this is G. And where will be inductive susceptance? Minus J.5. This is 0.5. Capacitive susceptance 0.2. This is capacitive susceptance. According to that, you will be getting the currents. According to that, you will be getting currents. How do you take up the current division? We have seen already current division. IR is equals to entering current into, how do you take up entering current? Entering current simply IS is equal to 3 at an angle 60 degrees. 3 at an angle 60 degrees. Okay. 3 at an angle 60 degrees. So entering current into which current you wanted to calculate? IR. IR, if you wanted to calculate, remove that resistance and other two resistors. That is J2 into minus J5 divided by R1 R2 plus R2 R3 plus R1 R3. So that is 1.2 into J2 plus 1.2 into minus J5 plus J2 into minus J5. For everything, just now already we did the same procedure in the same manner you can do. After doing this one, you will get IR magnitude and phase. So in the same manner, if it is leading, you go ahead with the leading. If it is lagging, go ahead with the lagging. You can get it. I'll show you the phasor diagram also. How do you get phasor diagram? Voltage, I am taking voltage as reference because VR, VL, VC all are same. In parallel connection, all are same. Voltage across resistance, voltage across inductance, voltage across capacitance. Now, how will be the current? Current is going to be like this. Current will be in phase. How will be the inductor? Inductor current will be like this. Let me draw here also. So you have to see whether the inductor current magnitude is greater or capacitor current magnitude is greater. Obviously, here this magnitude is greater. Capacitive reactance magnitude is greater. Inductive capacitive current is going to be smaller value compared to IL is going to be greater than IC because XL is less than XC. Lesser the impedance, more the current, right? So this is IL and this is parallelly I can write. And where is IC? IC will be here. Let me take up IC. And this is my IC. So in parallel. You can draw either here, you can draw at the end, you can draw at the beginning. Any issue? No issues. Now, IL and IC are quite opposite. So IC and IL can be compensated. So you are going to get IL minus IC. Now, IL minus IC and IR, this resultant is going to be the source current. So definitely the source current is lagging with respect to source voltage by some angle. Source voltage by some angle. Okay. Why? Because inductive reactance is 2 ohms and capacitive reactance of 5 ohms. But here inductive current, the inductive nature is going to draw large current than the capacitive current. According to that, I can say inductive dominating nature is inductive nature. Current lags the voltage. Okay. So source current, and this is a source current, and this is IL minus IC, and this is IL, and this is IC. If you see from the source current, if you see the other way, IL is lagging with respect to IS by some angle. See, IC with respect to source current, IC is leading by some angle. So when you solve it, you will get the answers. When you solve it, you will get the answers. When you are solving now, so this is IR. This IR with respect to source current, you will get definitely this is IR na. So from from source current, if you move to IR is leading with respect to source current. Definitely you will get some R at an angle theta, positive angle. But for inductor current is lagging with respect to source current. You will get negative angle. Okay. So these are the points you need to observe. That is the thing I have given for RL nature, RC nature. So in the same procedure you can apply for RLC also. Okay. So right, fine. Here find the unknown element. Find the unknown element, and circuit has a lagging power factor, means definitely more inductive nature. So see that which element is going to be. Find the unknown element, and is saying that average power to the circuit is 3000 watts. P is 3000 watts. That means what? E into I into cos phi. I also we know, E also we know. The angle between E and Y, obviously you can calculate. This is 3000 is equal to 100 and 40. So you can calculate easily power factor. Anyhow, he's saying lagging power factor, so definitely inductive nature element you have to take out. You see now. Okay. All right. So this is how calculations will be. We will take up some more the combinations like series parallel combination, DC circuits, series parallel combinations of AC circuits we will see, and there I'll try to give each and every component, power component also, so that you will explore much things. All right, so that's all for the day today. Have a nice day. In the next session we will discuss, I think tomorrow we have applications of series and parallel circuits. So we'll be taking it for a small duration only, hardly not more than 40 minutes, because applications I just wanted to tell you, and how you can check also, how you can troubleshoot also. Troubleshooting technique also we will try to find out. Applications of series and parallel circuits and troubleshooting technique. So whenever it fails, how do you find out the place? How do you identify the place and how do you clear it? Rectification of fault simply. Okay. All right. So thank you so much. Have a nice day. So if you have any problems, you can reach me on Telegram channel. You can post your doubts onto the Telegram channel. so that I can try to respond. Okay, my dear. Thank you. Thank you, everyone. Have a nice day. Bye bye. See you.